Welcome to this introductory course on containers and Kubernetes. My name is Alex Parker.
And I'm Okhar Litter. This course was made for anybody who wants to learn how to design, develop, deploy, manage secure applications on public, private, and hybrid cloud platforms. By the end of this course, you will not only have a running application on public cloud, but also have a really good understanding of Kubernetes and containers.
Containerization is not a new technology, but it rose to greater prominence in 2013 with the release of Docker, and it hasn't stopped growing since. In fact, containers have become the technology for modern cloud-native development. The analyst firm Gartner predicts that by 2023, over 70% of global organizations will be running more than 2 containerized applications in production, up from less than 20% in 2019. The Cloud Native Computing Foundation, known as CNCF, conducts annual surveys to discern where and how cloud-native technologies are being adopted. The 2019 survey indicates that 84% of respondents are using containers in production, up from 74% in 2018 and 23% in the first survey in 2016. These trends clearly demonstrate that containers aren't a passing fad or a niche technology, but an industry-changing revolution that will impact organizations small and large and developers worldwide.
Likewise, Kubernetes, an open source platform for orchestrating running containers, was developed and contributed to the open source community by Google in 2015. The Cloud Native Computing Foundation did a survey in 2019 and found that the number of users or respondents who were interested in cloud native computing technologies went up from 58% to 78% from the previous year. Kubernetes is the third largest platform for number of committers on GitHub, as well as second largest for number of issues and pull requests, only after the Linux kernel. A thriving ecosystem surrounds the open source Kubernetes platform, including applications for cloud security, service mesh, as well as other cloud native technologies. As a result of these things, Kubernetes and containers have become the de facto standards when talking about cloud-native applications, also making them the foundation for any cloud computing-related learning.
This course will introduce you to containers, Docker, and container registries to get you started with the foundations of this technology. Then you'll learn about the need for container orchestration, in Kubernetes specifically, including its architecture, the different resources you can deploy in Kubernetes, and how to put those pieces together to deploy a working application. And finally, you'll learn about the Kubernetes ecosystem, including Red Hat OpenShift and Istio, and how these tools can make your journey to containerization and your subsequent use of containers so much better.
The course contains several hands-on labs that will help you apply the content you learn. If you do not have the resources to set up a Kubernetes cluster, the course will provide an environment free of charge, which will help you to finish the labs.
The prerequisites for this course include basic computer and cloud literacy, as well as an understanding of core cloud concepts. In addition, understanding of the command line and how to use shell commands will greatly benefit you during this course. Let's get started.
Let's get started.
Welcome to Introduction to Containers. After watching this video, you will be able to identify the traditional computing issues for software development, define a container and describe its characteristics, and list container benefits and challenges and popular container vendors. Cloud Native is the newest application development approach for building scalable, dynamic, hybrid cloud-friendly software. And container technology is a powerful part of that approach. Let's check out the analogy of a shipping container. The modern shipping industry standardized a set of container sizes, so no matter what item is shipped, the container size remains the same. Standardization significantly improves shipping efficiency. Logistics staff select container transport options, such as ships, planes, trains, and trucks, based on the container size and the client's delivery needs. Digital container technology is similar. Containers solve the problem of making software portable so that the applications can run on multiple platforms. A container powered by the containerization engine is a standard unit of software that encapsulates the application code, runtime, system tools, system libraries, and settings necessary for programs to build, ship, and run applications efficiently. Operations and underlying infrastructure issues are no longer blockers. You can quickly move applications from your laptop to a testing environment, from a staging environment to a production environment, from a physical machine to a virtual machine, or a private cloud or public cloud, and always know that your application will work correctly. A container can be small, just tens of megabytes, and developers can almost instantly start containerized applications. With these capabilities, containers serve as the foundation for today's development and deployment solutions standards. Let's examine some of the development and deployment challenges organizations encounter with traditional computing environments. In traditional environments, developers can't isolate the app and allocate or designate specific storage and memory resources for apps on physical servers. Servers are often underutilized or overutilized, leading to poor utilization and a poor return on investment. Traditional deployments require comprehensive provisioning resources and expensive maintenance costs. The limits of physical servers can constrain application performance during peak workloads. Applications are not portable across multiple environments and operating systems. Implementing hardware for resiliency is often time-consuming, complex, and expensive. Traditional on-premises IT environments have limited scalability. And finally, automation is challenging when distributing software to multiple platforms and resources using traditional environments. Containers enable organizations to overcome these challenges. Container engines virtualize the operating system and are responsible for running containers. Platform-independent containers are lightweight, fast, isolated, portable, and secure, and often require less memory space. Binaries, libraries, and other entities within the container enable apps to run, and one machine can host multiple containers. Containers help programmers quickly deploy code into applications. Containers are platform-independent and can run on the cloud, desktop, and on-premises. Containers, being operating system independent, run on Windows, Linux, or Mac OS. Containers are also programming language and IDE independent, whether you are running Python, Node, Java, or other languages. Containers enable organizations to quickly create applications using automation, lower deployment time and costs, improve resource utilization including CPU and memory, port across different environments, and support next-gen applications including microservices. Now, using containerization is not without its challenges. Server security can become an issue if its operating system is affected. Developers can become overwhelmed when managing thousands of containers. Converting monolithic legacy applications can be a complex process, and developers can experience difficulty right-sizing containers for specific scenarios. Next, let's learn about some of the more popular container vendors. Docker is a robust platform and the most popular container platform today. Podman is a daemonless container engine that is more secure than Docker. Developers often prefer LXC for data-intensive applications and operations, and Vagrant offers the highest levels of isolation on the running physical machine. In this video, you learned that organizations are moving to containers to overcome challenges around isolation, utilization, provisioning, performance, and more. A container is a standard unit of software that encapsulates everything needed to build, ship, and run applications. Containers are operating system, programming language, and platform independent. They lower deployment time and costs, improve utilization, automate processes, and support next-gen applications or microservices. Developers may find that management, legacy project migration, and right-sizing are significant challenges. And finally, major container vendors include Docker, Podman, LXC, and Vagrant.
Welcome to Introduction to Docker. After watching this video, you will be able to define what Docker is, describe the Docker process and underlying technology, list the benefits of Docker containers, and identify the challenges of Docker containers. Available since 2013, the official Docker definition, paraphrased, states that Docker is an open platform for developing, shipping, and running applications as containers. Docker became popular with developers because of its simple architecture, massive scalability, and portability on multiple platforms, environments, and locations. Docker isolates applications from infrastructure, including the hardware, the operating system, and the container runtime. Docker is written in the Go programming language. Docker uses Linux kernel features to deliver its functionality. Docker also uses namespaces to provide an isolated workspace called the container. And Docker creates a set of namespaces for every container, and each aspect runs in a separate namespace, with access limited to that namespace. Docker methodology has inspired additional innovations, including complementary tools such as Docker CLI, Docker Compose, and Prometheus, and various plugins, including storage plugins. Orchestration technologies using Docker Swarm or Kubernetes, and development methodologies using microservices and serverless. Docker offers the following benefits. Docker's consistent and isolated environments result in stable application deployments. Deployments occur in seconds. Because Docker images are small and reusable, they significantly speed up the development process. And Docker automation capabilities help eliminate errors, simplifying the maintenance cycle. Docker supports Agile and CI/CD DevOps practices. Docker's easy versioning speeds up testing, rollbacks, and redeployments. Docker helps segment applications for easy refresh, cleanup, and repair. Developers collaborate to resolve issues faster and scale containers when needed. And Docker images are platform independent, so they are highly portable. Docker is not a good fit for applications with these qualities. Require high performance or security, are based on monolith architecture, use rich GUI features, or perform standard desktop or limited functions. In this video, you learn that Docker is an open platform for developing, shipping, and running applications as containers. Docker speeds up the deployment process across multiple environments. Docker uses namespaces technology to provide an isolated workspace called the container. Docker creates a set of namespaces for every container, and each aspect runs in a separate namespace with access limited to that namespace. Docker supports Agile and CI/CD DevOps practices. And lastly, Docker containers are not a good fit for applications based on monolithic architecture or applications that require high-performance security. Welcome to Building and Running Containers. After watching this video, you will be able to build a container image using a Dockerfile, create a running container using an image, and describe key Docker commands. This diagram shows the development process of a running container. The steps to create and run containers are: create a Dockerfile, use the Dockerfile to create a container image, and use the container image to create a running container. Use a Dockerfile to create a running container. This sample Dockerfile has the commands from and cmd. From defines the base image, and cmd prints the words "Hello World" on the terminal. You'll notice that this Docker command uses the build command, the tag, the repository, the version, and the current directory. After you run this build, the output messages include sending build context to Docker daemon, successfully built image, which confirms image creation, and successfully tagged my app, which confirms the tag. To verify the creation of the image, run the Docker images command. The output displays the repository, my app, as well as the tag, v1, image ID, creation date, and the image size. Create the container using the run command with the container image name and tag. The application prints the words, "Hello World," execute the Docker PSA command, which displays the details of the container created. Given the appropriate input, the build command is used to create container images with tags from a Dockerfile. The images command will list all the images, their repositories and tags, and their sizes. The run command creates and runs a container from an image. The push command stores images in a configured registry, and the pull command retrieves images from a configured registry. In this video, you'll learn that the build command is used with a Dockerfile to build a container image. The run command is used with an image to create a running container. And key Dockerfile commands include build, images, run, pull, and push. Welcome to Introduction to Docker Objects. After watching this video, you will be able to identify and describe Docker objects, identify essential Dockerfile commands, explain container image naming, and describe how Docker uses networks, storage, and plugins. Docker contains objects such as Dockerfile, images, container, network, stored volumes, and other objects such as plugins and add-ons. A Dockerfile is a text file that contains instructions needed to create an image. You can create a Dockerfile using any editor from the console or terminal. Let's go over several of the essential instructions that Docker provides. A Dockerfile must always begin with a from instruction that defines a base image. Often the base image is from a public repository, like an operating system or a specific language like Go or Node.js. The run instruction executes commands. The CMD instruction defines a default command for execution. A Dockerfile should have only one CMD instruction. If the Dockerfile has several CMD instructions, only the last CMD instruction will take effect. Next, let's learn about Docker images. A Docker image is a read-only template with instructions for creating a Docker container. The Dockerfile provides instructions to build the image, and each Docker instruction creates a new layer in the image. When you change the Dockerfile and rebuild the image, the Docker engine only rebuilds the changed layers. Images can share these layers, which saves a lot of disk space, as well as network bandwidth when sending and receiving images. When you instantiate this image, you get a running container. At this point, a writable container layer is placed on top of the read-only layers, and the writable layer is needed because containers are not immutable as images. Now, let's learn about how images are named. An image name has a unique format that consists of three parts: the hostname, the repository, and the tag. The hostname identifies the image registry. A repository is a group of related container images, and the tag provides information about a specific version or variant of an image. Consider the image name docker.io/ubuntu:18.04. The hostname docker.io refers to the Docker Hub registry. When using the Docker CLI, you can exclude the docker.io hostname. The repository name Ubuntu indicates the Ubuntu image. Finally, the tag, shown here as 18.04, represents the installed Ubuntu version. Now, let's learn about Docker containers. What is a Docker container? A Docker container is a runnable instance of an image. You can use the Docker API or CLI to create, start, stop, or delete an image. You can connect to multiple networks, attach storage to the container, or create a new image based on its current state. Docker keeps containers well isolated from each other and their host machine. When using Docker, networks help isolate container communications. By default, data doesn't persist when the container no longer exists. Docker uses volumes and bind mounts to persist data even after a container stops. And plugins, such as storage plugins, provide the ability to connect to external storage platforms. In this video, you'll learn that Docker contains objects such as Dockerfiles, images, containers, networks, storage volumes, and other objects, such as plugins and add-ons. Essential Docker instructions include from, run, and CMD. A Docker container is a runnable instance of an image. An image name format consists of 3 identifiers: the host name, the repository, and the tag. Docker uses networks to isolate container communications. Docker uses volumes and bind mounts to persist data even after a container stops running. And plugins, such as storage plugins, provide the ability to connect to external storage platforms. Hello, and welcome to Docker Architecture. After watching this video, you will be able to identify the components of the Docker architecture, explain the features of the Docker architecture components, and describe the process of containerization using Docker. The Docker client-server architecture provides a complete application environment. Docker components include the client, the host, and the registry. Let's take a high-level view of how Docker works. First, you'll use either the Docker command line interface or REST APIs via the Docker client to send instructions to the Docker host server, commonly called the host. The Docker host contains the daemon, known as Dockered. The daemon listens for Docker API requests or commands such as Docker run and processes those commands. The daemon does the heavy lifting to build, run, and distribute Docker containers. Then, Docker stores the container images in a registry. The Docker host also includes and manages images, containers, namespace, networks, storage, plugins, and add-ons. You can use the Docker client to communicate with local and remote Docker hosts. You can run the Docker client and daemon on the same system, or connect your Docker client to a remote Docker daemon. And Docker daemons can also communicate with other daemons to manage Docker services. Docker stores and distributes images in a registry. Registry access is either public, such as Docker Hub, which is accessible by everyone, or private. Enterprises usually opt to use a private registry for security reasons. And registry locations are hosted using a third-party provider, such as IBM Cloud Container Registry, or self-hosted in private data centers or on the cloud. Next, let's learn about moving images into the registry. First, developers build and push the images using automation or a build pipeline into a registry, where Docker stores these images. Then, local machines, cloud systems, and on-premises systems can pull those images. Let's examine the process in more detail. Here is a visual representation of the Docker architecture, which consists of the client, the Docker host, including the Docker daemon, and the registry with its existing stored images. Let's check out the containerization process. Here's how you use Docker to create a container image. First, use an existing base image or a Dockerfile. Then, issue the build command that creates a container image with a name. Next, issue the push command to store the image to the registry. The host first checks locally if the image is already available, and then issues the run command with the image name to create the container. If the image is unavailable within the host, the Docker client connects to the registry and pulls the image to the host. The daemon then creates a running container using the image. In this video, you learn that Docker architecture consists of a Docker client, a Docker host, and a registry. The client interacts with the host using commands and REST APIs. The Docker host includes the daemon, commonly called Dockered. The Docker host also manages images, containers, namespaces, networks, storage, plugins, and add-ons. And containerization is the process used to build, push, and run an image to create a running container. Welcome to Container Orchestration. After watching this video, you will be able to define the challenges of container management, determine when container orchestration is needed, and demonstrate container orchestration benefits. Everyone's container journey starts with one container. However, things don't stay this way for long. Over time, new applications are written and projects are deployed globally to increase availability. That one initial container inevitably becomes several containers. And initially, that growth is easy to handle, but soon it's overwhelming. Consider connecting, managing, and scaling hundreds or thousands of containers into a large application like a database or web app. This can easily get out of control. To create scale and manage large numbers of containers, container orchestration is needed. Container orchestration is a process that automates the container lifecycle of a container-based or containerized application. This includes deployment, management, scaling, networking, and availability. Container orchestration is necessary in large dynamic environments since it streamlines complexity, enables hands-off deployment and scaling, increases speed, agility, and efficiency, seamlessly integrates into CI/CD workflows and DevOps practices, and allows development teams to use resources more efficiently. Container orchestration can be implemented on premises and on public, private, or multi-cloud environments. It is often a critical part of an organization's security, orchestration, automation, and response requirements, also known as SOAR requirements. Container orchestration tools have a wide variety of features. These features include defining which container images make up the application and where they are located, in what registry, improving provisioning and deployment of containers for a more automated, unified, and smooth process, securing network connections between containers, ensuring availability and performance by relocating the containers to another host if an outage or shortage of system resources occurs, scaling containers to meet demand and load balance requests, handling resource allocation and scheduling of containers to the underlying infrastructure, performing rolling updates and rollbacks, and conducting health checks to ensure applications are running or performing the necessary actions when checks fail. Container orchestration uses configuration files written in YAML or JSON. These files configure each container so it can find resources, establish a network, and store logs. Container orchestration also automatically schedules the deployment of a new container to a cluster and finds the right host based on predefined settings or restrictions. Additionally, container orchestration manages the container's lifecycle based on specifications in the configuration file. This includes system parameters, like CPU and memory, and file parameters, like proximity and file metadata. And container orchestration supports scaling and enhances productivity through automation. Here are some well-known container orchestration tools. Marathon is a framework for Apache Mesos, an open-source cluster manager that was developed by the University of California at Berkeley. It allows you to scale container infrastructure by automating the bulk of management and monitoring tasks. HashiCorp's Nomad is a free and open-source cluster management and scheduling tool that supports Docker and other standalone, virtualized, or containerized applications on all major operating systems across all infrastructure, whether on-premises or in the cloud. This flexibility lets teams work with any type and level of workload. Docker Swarm automates the deployment of containerized applications, but was designed specifically to work with Docker Engine and other Docker tools, making it a popular choice for teams already working in Docker environments. Developed by Google and maintained by the Cloud Native Computing Foundation, CNCF, the open-source platform Kubernetes is the de facto standard for container orchestration. Kubernetes automates a host of container management tasks, including deployment, storage provisioning, load balancing and scaling, service discovery, and self-healing, the ability to restart, replace, or remove a failed container. With broad functionality and an expanding ecosystem of open-source supporting tools, Kubernetes is widely supported by leading cloud providers, many of whom now offer fully managed Kubernetes services. Container orchestration helps to meet business goals and increase profitability by using automation. The benefits of container orchestration for developers and administrators include increased productivity, removing the burden of individually installing and managing each container, which in turn reduces errors and frees development teams to focus on application improvement. Faster deployments, iteratively releasing new features and capabilities faster and deploying containers and containerized applications rapidly. Reduced costs. Being cost-effective, service containers have lower overhead and use fewer resources than virtual machines or traditional servers. Stronger security, sharing resources and isolating application processes, improving the container's overall security. Easier scalability, scaling applications using a single command and faster error recovery. Maintaining high availability by detecting and resolving issues like infrastructure failures automatically. In this video, you learn that managing large numbers of containers is difficult. Container orchestration automates the container lifecycle, resulting in faster deployments, reduced errors, higher availability, and stronger security. Popular container orchestration tools include Marathon, Nomad, Docker Swarm, and Kubernetes. And finally, container orchestration improves productivity, deployment, costs, security, scalability, and error recovery. Welcome to Introduction to Kubernetes. After watching this video, you will be able to define Kubernetes, explain what Kubernetes is not, relate Kubernetes concepts, describe Kubernetes capabilities, and describe the Kubernetes ecosystem. The official Kubernetes documentation describes Kubernetes as an open-source system for automating deployment, scaling, and management of containerized applications. Kubernetes is widely available and has positioned itself as the de facto choice for container orchestration. Kubernetes is an open-source containerization orchestration platform developed as a project by Google and is currently maintained by the Cloud Native Computing Foundation. It is easily portable across clouds and on-premises. With its growing ecosystem of projects and products by both member and non-member partners, Kubernetes is recognized as the go-to container orchestration solution. Kubernetes as a service grew as an extension of containers as a service. Kubernetes facilitates declarative management, in which it automatically performs the necessary operations towards achieving the called-for state. Here's what Kubernetes is not. It is not a traditional all-inclusive platform as a service. It is not rigid or opinionated, but more of a flexible model that supports an extremely diverse variety of workloads, including stateless, stateful, and data processing workloads. It can work with all applications that can be containerized. It does not provide continuous integration, continuous delivery pipelines to build applications or deploy source code. It does not prescribe logging, monitoring, and alerting solutions. Organizations are free to select and integrate third-party and open-source tools. And it does not provide built-in middleware, databases, or other services. Let's check out some Kubernetes concepts. Concepts of Kubernetes include the following. Pods represent the smallest deployable compute object and the higher-level abstractions to run workloads. Services expose applications running on sets of pods. Each pod is assigned a unique IP address, and sets of pods have a single DNS name. Kubernetes supports both persistent and temporary storage for pods. Configuration, which refers to the provisioning of resources for configuring pods. Security measures for cloud-native workloads, which enforce security for pod and API access. Policies for groups of resources, ensuring that pods match to nodes so that the kubelet can find them and run the pods. Scheduling and eviction that runs and proactively terminates one or more pods on resource-starved nodes. Preemption, which is all about prioritization. Preemption terminates lower priority pods so that pods with higher priority can schedule and run on nodes. And finally, cluster administration provides the details necessary to create or administer a cluster. Kubernetes capabilities include automated rollouts of changes to application or configuration, health monitoring, and rolling back changes. Storage orchestration that mounts a chosen storage system, including local storage, network storage, or public cloud. And horizontal scaling of workloads based on metrics or via commands. Additional capabilities include the following. Automated bin packing that increases utilization and cost saving using a mix of critical and best effort workloads. Automated bin packing performs container auto-placement based on resource requirements and conditions without sacrificing high availability. Kubernetes includes secret and configuration management of sensitive information, including passwords, OAuth tokens, and SSH keys, and handles deployments and updates to secrets and configuration without rebuilding images. And Kubernetes assigns both IPv4 and IPv6 addresses to pods and services. Kubernetes manages batch and continuous integration workloads and automatically replaces failed containers. It self-heals failing or unresponsive containers. It discovers pods using IP addresses or a DNS name and load balances traffic for better performance and high availability. And Kubernetes adds features to your cluster without modifying source code. The Kubernetes ecosystem is a large, rapidly growing ecosystem where its services, support, and tools that are widely available. Running containerized applications requires separate tools in addition to the Kubernetes orchestration tool. The ecosystem includes services like building container images, storing images in a container registry, application logging and monitoring, and CI/CD capabilities. The Kubernetes ecosystem is a huge collection of products, services, and providers. Leading public cloud providers include Prisma, IBM, Google, and AWS. Open source framework providers include Red Hat, VMware, SUSE, Mesosphere, Docker, and Cloud Foundry. Management providers include DigitalOcean, Lutz, Supergiant, CloudSoft, Turbonomic, Tectonic, and Weaverworks. Tool providers include JFrog, Univa, Aspen Mesh, Bitnami, and Cloud66. Monitoring and logging providers include Sumo Logic, Datadog, New Relic, Iguazio, Grafana Signal FX, Sysdig, and Dynatrace. Security providers include GuardCore, BlackDuck, Yubico, Kilium, Aqua, Twistlock, and Alcide. And load balancing providers include AVI Networks, VMware, and Nginx. In this video, you learn that Kubernetes is a highly portable, horizontally scalable, open-source container orchestration system with automated deployment and simplified management capabilities. Its concepts include pods and workloads, services, storage, configuration, security, policies, scheduling and eviction, preemption, and administration. You also learn that Kubernetes capabilities include automated rollouts and rollbacks, storage orchestration, horizontal scaling, automated bin packing, secret and configuration management, IPv4, IPv6 dual stack support, batch execution, self-healing, service discovery and load balancing, and finally, designed for extensibility. And the Kubernetes ecosystem includes public cloud providers, frameworks, management, tools, monitoring and logging, security, and load balancing. Welcome to Kubernetes architecture. After watching this video, you will be able to identify the components of a Kubernetes architecture, identify the components of a control plane, and identify the components of a worker plane. This architecture diagram highlights the main components in a Kubernetes system. A deployment of Kubernetes is called a Kubernetes cluster. A Kubernetes cluster is a cluster of nodes that runs containerized applications. Each cluster has one master node, the Kubernetes control plane, and one or more worker nodes. The control plane maintains the intended cluster state by making decisions about the cluster and detecting and responding to events in the cluster. As an analogy, it is similar to a thermostat. You specify the desired temperature, and the thermostat regulates heating and cooling systems continuously to achieve the specified state. An example of a decision made by the control plane is the scheduling of workloads. And an example of responding to an event is creating new resources when an application is deployed. Nodes are the worker machines in a Kubernetes cluster. In other words, user applications are run on nodes. Nodes are not created by Kubernetes itself, but rather by the cloud provider. This allows Kubernetes to run on a variety of infrastructures. The nodes are then managed by the control plane. In the Kubernetes control plane, the Kubernetes API server exposes the Kubernetes API. The API server serves as the front end for the control plane. All communication in the cluster utilizes this API. For example, the Kubernetes API server accepts commands to view or change the state of the cluster. The main implementation of a Kubernetes API server is kube app-server, which is designed to scale horizontally by deploying more instances. You can run several instances of kube app-server and balance traffic between those instances. etcd is a highly available distributed key value store that contains all the cluster data. When you tell Kubernetes to deploy your application, that deployment configuration is stored in etcd. etcd defines the state in a Kubernetes cluster, and the system works to bring the actual state to match the desired state. The Kubernetes scheduler assigns newly created pods to nodes. This basically means that the kube scheduler determines where your workloads should run within the cluster. The scheduler selects the most optimal node according to Kubernetes scheduling principles, configuration options, and available resources. The Kubernetes controller manager runs all the controller processes that monitor the cluster state and ensure the actual state of a cluster matches the desired state. Finally, the cloud controller manager runs controllers that interact with the underlying cloud providers. These controllers effectively link clusters into a cloud provider's API. Since Kubernetes is open source and would ideally be adopted by a variety of cloud providers and organizations, Kubernetes strives to be as cloud agnostic as possible. The Cloud Controller Manager allows both Kubernetes and the cloud providers to evolve freely without introducing dependencies on the other. Nodes are the worker machines in a Kubernetes cluster. In other words, user applications are run on nodes. Nodes can be virtual or physical machines. Each node is managed by the control plane and contain the services necessary to run applications. Nodes include pods, which are the smallest deployment entity in Kubernetes. Pods include one or more containers. Containers share all the resources of the node and can communicate among themselves. The kubelet is the most important component of a worker node. This controller communicates with the kube API server to receive new and modified pod specifications and ensure that the pods and their associated containers are running as desired. The kubelet also reports to the control plane on the pod's health and status. And in order to start a pod, the kubelet uses the container's runtime. The container runtime is responsible for downloading images and running containers. Rather than providing a single container runtime, Kubernetes implements a container runtime interface that permits pluggability of the container runtime. While Docker is likely the best-known runtime, Podman and Creo are two other commonly used container runtimes. Lastly, the Kubernetes proxy is a network proxy that runs on each node in a cluster. This proxy maintains network rules that allow communication to pods running on nodes. In other words, communication to workloads running on your cluster. In this video, you learned that a control plane makes global decisions about the Kubernetes cluster. A control plane is made up of controllers, an API server, a scheduler, and an etcd. A worker plane is made up of nodes, kubelet, container runtime, and kube proxy. Worker nodes run important Kubernetes components as well as user workloads deployed on the cluster. And the smallest deployable entity in Kubernetes is a pod, which includes one or more containers. Welcome to Kubernetes Objects Part 1. After watching this video, you will be able to define a Kubernetes object and its properties, describe basic Kubernetes objects and their features, and demonstrate how Kubernetes objects relate to each other. In the real world, an object is something that has an identity, a state, and a behavior. A window or a shopping cart are examples of objects. A software object is a bundle of data that has an identity, a state, and a behavior. Examples include variables, data structures, and specific functions. Another term is entity, which also has an identity and associated data. For example, in banking, a customer account is an entity. Finally, the term persistent means something will last even if there is a server failure or network attack. An example is persistent storage. Kubernetes objects are persistent entities. Examples include pods, namespaces, replica sets, deployments, and more. Kubernetes objects consist of two main fields, object spec and status. The object spec is provided by the user, which dictates an object's desired state. Status is provided by Kubernetes. This describes the current state of the object. Kubernetes works towards matching the current state to the desired state. To work with these objects, use the Kubernetes API directly with the client libraries and the kubectl command line interface, or both. Labels are key value pairs attached to objects. They are intended for identification of objects. However, a label does not uniquely identify a single object. Many objects can have the same labels, and this helps to organize and group objects. Label selectors are the core grouping method in Kubernetes. They allow you to identify a set of objects. Namespaces provide a mechanism for isolating groups of resources within a single cluster. This is useful when teams share a cluster for cost-saving purposes or for maintaining multiple projects in isolation. Namespaces are ideal when the number of cluster users is large. Examples of namespaces are kubesystem, intended for system users and the default namespace used to hold users' applications. There are different patterns of working with namespaces. There may be only one namespace for a user who works with one team which only has one project that is deployed into a cluster. Alternatively, there may be many teams or projects, or a lot of users with different needs, where additional namespaces may be created. Namespaces provide a scope for the names of objects. Each object must have a unique name for that resource type within that namespace. A pod is the simplest unit in Kubernetes. A pod represents a process or a single instance of an application running in the cluster. A pod usually wraps one or more containers, and creating replicas of a pod serves to scale an application horizontally. YAML files are often used to define the object that you want to create. The YAML file shown defines a simple pod. The kind field specifies the kind of object to be created. In this case, we create a pod. The spec field provides the appropriate fields for the object to be created, such as the containers that will run in this pod. A pod spec must contain at least one container. In this example, the container is named Nginx. The image field dictates which image will run in the pod, and the ports array lists the ports that the container exposes. A replica set is a set of identical running replicas of a pod that are horizontally scaled. The configuration files for a replica set and a pod are different from each other. The replicas field specifies the number of replicas that should be running at any given time. Whenever this field is updated, the replica set creates or deletes pods to meet the desired number of replicas. A pod template is included in the replica set spec, which defines the pods that should be created by the replica set. Under the selector field, the labels supplied in the match labels field specify the pods that can be acquired by the replica set. Notice that the label identified in the match labels field is the same as the labels field in the pod template. Both are the app Nginx. Creating replica sets directly is not recommended. Instead, create a deployment, which is a higher-level concept that manages replica sets and offers more features and better control. A deployment is a higher-level object that provides updates for both pods and replica sets. Deployments run multiple replicas of an application using replica sets and offer additional management capabilities on top of these replica sets. Deployments are suitable for stateless applications. For stateful applications, stateful sets are used. Examples of deployments include the deployment of a replicated application, pod updates managed by a deployment, or the scaling up of an application. This deployment specification example shows the kind is deployment, which defines the number of replicas, a selector to identify which pods can be acquired, and a pod template. One key feature provided by deployments but not replica sets is rolling updates. A rolling update scales up a new version to the appropriate number of replicas and scales down the old version to 0 replicas. The replica set ensures that the appropriate number of pods exist, while the deployment orchestrates the rollout of a new version. In this video, you learn that Kubernetes objects are persistent entities. Their main fields are object spec and status. Namespaces help in isolating groups of resources within a single cluster. Pods represent a process or an instance of an app running in the cluster. Replica sets create and manage horizontally scaled running pods, and deployments provide updates for pods and replica sets. Welcome to Kubernetes Objects, Part 2. After watching this video, you will be able to describe the purposes, properties, and uses of a service. Describe the roles and uses for the cluster IP, node port, load balancer, and external name services. And describe the roles and uses for ingress, daemon set, stateful set, and a job. A service is a REST object, like pods. Services are a logical abstraction for a set of pods in a cluster. They provide policies for accessing the pods in cluster and act as a load balancer across the pods. Each service is assigned a unique IP address for accessing applications deployed on pods, and a service eliminates the need for a separate service discovery process. A service supports multiple protocols, such as TCP, which is the default protocol, UDP, and others, and supports multiple port definitions. The port number with the same name can vary in each backend pod. In addition, a service can have an optional selector and can optionally map incoming ports to a target port. Next, let's learn why a service is needed. A service is needed because pods in a cluster can be destroyed, and new pods can be created at any time. This volatility leads to discoverability issues because of changing IP addresses. A service keeps track of pod changes and exposes a single IP address or a DNS name and utilizes selectors to target a set of pods. For native Kubernetes applications, API endpoints are updated whenever changes are detected to the pods in the service. For non-native applications, Kubernetes uses a virtual IP-based bridge or load balancer in between the applications and the backend pods. There are 4 types of services: cluster IP, node port, load balancer, and external name. Let's learn about each service type. Cluster IP is the default and most common service type. Kubernetes assigns a cluster internal IP address to the cluster IP service that makes the service only reachable within the cluster. A cluster IP service cannot make requests to service from outside the cluster. You can set the cluster IP address in the service definition file, and the cluster IP service provides inter-service communication within the cluster. For example, communication between the front-end and back-end components of your app. An extension of cluster IP service, a node port service, creates and routes the incoming requests automatically to the cluster IP service. A node port exposes the service on each node's IP address at a static port. Note that for security purposes, production use is not recommended. Kubernetes exposes a single service with no load balancing requirements for multiple services. An extension of the node port service, an external load balancer, or ELB, creates node port and cluster IP services automatically. An ELB integrates and automatically directs traffic to the node port service. To expose a service to the internet, you need a new ELB with an IP address. You can use a cloud provider's ELB to host your cluster. The external name service type maps to a DNS name and not to any selector, and requires a spec.externalName parameter. The external name service maps the service to the contents of the external name field that returns a CNAME record and its value. You can use an external name to create a service that represents external storage and enables pods from different namespaces to talk to each other. Next, ingress is an API object that, when combined with a controller, provides routing rules to manage external users' access to multiple services in a Kubernetes cluster. In production, ingress exposes applications to the internet via port 80 for HTTP or port 443 for HTTPS. While the cluster monitors ingress, an external load balancer is expensive and is managed outside the cluster. A daemon set is an object that makes sure that nodes run a copy of a pod. As nodes are added to a cluster, Pods are added to the nodes. Pods are garbage collected when removed from a cluster. If you delete a daemon set, all pods are removed. Daemon sets are ideally used for storage, logs, and monitoring nodes. A stateful set is an object that manages stateful applications, manages deployment and scaling of pods, and provides guarantees about the ordering and uniqueness of pods. A stateful set maintains a sticky identity for each pod request and provides persistent storage volumes for your workloads. And lastly, a job creates pods and tracks the pod completion process. Jobs are retried until completed. Deleting a job will remove the created pods. Suspending a job will delete its active pods until the job resumes. A job can run several pods in parallel. And cron jobs are regularly used to create jobs on an iterative schedule. In this video, you learn that a service in Kubernetes is a REST object that provides policies for accessing the pods and cluster. Cluster IP is the default and most common service type and provides inter-service communication within the cluster. An extension of cluster IP service, a node port service, creates and routes the incoming requests automatically to the cluster IP service. An extension of the node port service, an external load balancer creates node port and cluster IP services automatically. And ingress is an API object that, when combined with a controller, provides routing rules to manage external users' access to multiple services in a Kubernetes cluster. You also learn that using a daemon set ensures that there is at least one instance of the pod on all your nodes. You can use external name to create a service that represents external storage and enables pods from different namespaces to talk to each other. A stateful set manages stateful applications, manages pod deployment and scaling, maintains a sticky identity for each pod request, and provides persistent storage volumes for your workloads. And finally, a job creates pods and tracks the pod completion process. Jobs are retried until completed. Welcome to Using Kubectl. After watching this video, you will be able to define Kubectl and the command structure, list the 3 command types, their features and advantages, and list commonly used commands with specific examples. Kubectl is the Kubernetes Command Line Interface, or CLI. Kubectl stands for Kube Command Tool Line. Kubectl is one of the key tools for working with Kubernetes, and it helps users deploy applications, inspect and manage cluster resources, view logs, and more. It provides many features for users who work with Kubernetes clusters and manage running cluster workloads. And 3 Kubectl command types are imperative commands, imperative object configuration, and declarative object configuration. Kubectl commands use the following structure. Keeping each component in order is critical. Command means any operation to be performed, like create, get, apply, or delete. Type means resource type, like pod, deployment, or replica set. Name means resource name, if applicable. And flags means special options or modifiers that override default values. Imperative commands allow you to create, update, and delete live objects directly. Operations should be specified to the command as arguments or flags. Imperative commands are easy to learn and run. For example, to create a pod with a specific container, simply run the command as shown, specifying only a pod name and the container image. But imperative commands don't provide an audit trail, which is important for tracking changes. They aren't flexible since options are limited, they don't use templates, and they cannot integrate with change review processes. But they are ideal for development and test environments. Imperative commands do also have disadvantages. Suppose a developer runs a command to deploy an application. Another developer wants to deploy that same application, but they cannot because there is no configuration file. The second developer must check with the first developer for the exact command to deploy and then run it. It would be best if both developers used a template for the deployment since it overcomes the limitations of working with imperative commands. In imperative object configuration, the Kubectl command specifies required operations, optional flags, and at least one file name. The specified configuration file must contain a full definition of the objects in YAML or JSON format. To create the objects defined in the file, run the command kubectl create-f-nginx.yaml. Using the same configuration templates in multiple environments will produce identical results. A configuration file may be stored in a source control system like Git. It can integrate with change processes, and it provides audit trails and templates for creating new objects. But using it requires understanding of the object schema and requires writing a YAML or JSON file. Now, imperative object configuration also has limitations. You need to specify all necessary command operations. For example, if a developer performs an update operation that isn't merged into the configuration file, then another developer cannot use the updated configuration in future deployments. The second developer instead uses the original or previous configuration. It is better to define the desired state in a shared configuration file. Then when you deploy, Kubernetes automatically determines the necessary operations. This is known as declarative object configuration. Declarative object configuration stores configuration data in files. Operations are identified by kubectl instead of being specified by the user. This works on directories or individual files. For example, the kubectl apply command mentions a directory, as shown, then applies configuration data to all files in that directory. The user is not required to perform any operations since they are performed by the system automatically. Configuration files define a desired state, and Kubernetes actualizes that state. And this approach is the ideal method for production systems. Here's an example of declarative configuration. A developer performs updates to a running application. Since configuration data is stored in the shared template, there is still one source of truth for the configuration of this project. Now, even if another developer misses several of these updates, all they need to do is apply the current configuration template to ensure the deployed object is as expected. Kubernetes automatically determines and performs the necessary operations to match the current state to the desired state. Here are a few of the commonly used kubectl commands and descriptions. The get command accesses a file, container, or any other resource. The delete command deletes a file or container. The autoscale command applies the autoscaling process to the selected file or container, and so on. You can find all kubectl commands at kubernetes.io. Kubectl get commands allow you to list services in a current namespace, pods in all namespaces, a particular deployment, and pods in the current namespace. Kubectl apply commands create resources using YAML or JSON files. They use extensions like .yaml, .yml, or .json. You can use apply commands to create resources from multiple files or from a URL. Kubectl scale commands scale the number of replicas. You can use scale commands to scale a replica set named foo to 3 or a resource in foo.yaml to 3. Let's create a deployment with 3 replicas of the Nginx image. Create the deployment using the apply command. The output confirms the deployment creation. The get deployment command provides the specific mydep deployment details. The output confirms the creation of 3 replicas, ready, up to date, and available. In this video, you learn that kubectl is the Kubernetes command line interface. The kubectl command structure is kubectl, command, type, name, flags. Imperative commands are the easiest to learn, have no audit trail, and are not flexible. Imperative object configuration uses templates to ensure proper deployment replication. And finally, declarative object configuration is automated, requires no user input, and is ideal for production systems. Welcome to Replica Set. After watching this video, you will be able to define a replica set, explain how a replica set works, and list the benefits of using a replica set. If an application is deployed on a single pod, the pod will be unable to perform certain actions if requests increase manifold or outages occur. Single pod deployments cannot accommodate growing demands of the application and load balancing across pods, handle outages by eliminating a single point of failure, minimize downtime and service interruptions by providing high availability through redundant pods, or automatically restart deployments if something goes wrong. We can work around these limitations with a replica set. A replica set ensures the right number of pods are always up and running. It always tries to match the actual state of the replicas to the desired state. A replica set adds or deletes pods for scaling and redundancy, which helps maintain availability. It replaces failing pods or deletes additional pods to maintain the desired state. And it supersedes a replica controller and should be used instead. A replica set is created for when you create a deployment in your cluster. Deployments manage replica sets, send pods declarative updates, and have many other useful features. That's why a replica set is best managed by a deployment. Kubernetes is designed to keep object types independent. That is why the replica set does not own any of the pods. Instead, it uses pod labels to decide which pods to acquire when bringing a deployment to the desired state. Let's look at a deployment template. Here, the template metadata defines the labels and spec of potential pod candidates to add or delete. A replica set is automatically created for you when you create a deployment. To check this, create a deployment and then use a get replica set command to verify that the replica set is generated for you by default. The replica set only replicates to a single pod. Additionally, if you describe the pod, you will see the pod's details and that it is controlled by the same replica set. To create a replica set from scratch, apply a YAML file with the kind attribute set to replica set as shown. If you define the number of replicas as 1, you get 1 pod. This is similar to creating a default without specifying the number of replicas in your YAML file. Let's step through creating a replica set from scratch. First, use the create replica set command. The output shows a replica set was created. Confirm it was created by using the get pods command and observe the status as running. And then use the get rs command. RS is short for replica set. And the output shows the name and other details of the newly created replica set and its pod. But remember, creating a deployment that includes a replica set is recommended over creating a standalone replica set. Before you scale a deployment, you must ensure you have a deployment and a pod. To do this, create a deployment using the create command. The output will confirm a deployment was created. The deployment creates a pod by default, and you can confirm this with the get pods command. The output shows the pod name and other details. You can check the deployment details with the get deploy command. The output shows the deployment is named Hello Kubernetes. Now, once the deployment and pod are in place, use the scale command to scale the deployment and set the desired number of replicas. Here, we set the number of replicas to 3, and the output confirms the deployment is scaled. If you use the get pods command, you will see 3 pods running. The replica set created 2 new pods, one ending in 5MFLW and the other ending in HTB7V. Let's observe how the replica set maintains the desired state when the pod is deleted. First, use the get pods command. Our 3 pods appear in the output as expected. Now, use the delete pod command to delete the pod ending in 5MFLW. The pod ending in 5MFLW is deleted. And notice that the desired state does not match the actual state, and that the deleted pod is replaced by a new pod automatically. Now, use the get pods command again. The output shows the replica set immediately created a new pod ending in 6LW4R to get the total number of pods back to 3. The replica set maintains the desired state. Let's now observe how the replica set maintains desired state when a pod is created. The get pods command shows our 3 pods from before. Use the create pod command to create a pod ending in MX9RP. Then use the get pods command again, and the output now shows 4 pods. Desired state does not match actual state, Since the replica set always strives to match the actual state to the desired state, the new pod, ending in MX9RP, is marked for deletion and removed automatically. The getPods command now shows the total number of pods restored to 3. And once again, the replica set maintains the desired state. In this video, you learned that a replica set provides high availability through redundancy. A replica set enables scaling by creating or deleting pods. You can create a replica set using the CLI or the YAML descriptor. A replica set always tries to match the actual state to the desired state. And a best practice is to use a deployment instead of a replica set directly. Hello, and welcome to autoscaling. After watching this video, you will be able to define autoscaling, explain the 3 types of autoscalers, and demonstrate how each autoscaler works. Replica sets provide a good start for scaling, but you don't always want 10 instances of your resource running. You should be able to scale as needed. Kubernetes autoscaling helps optimize resource usage and costs by automatically scaling a cluster in line with demand. Kubernetes enables autoscaling at 2 different layers, the cluster or node level and the pod level. 3 types of autoscalers are available in Kubernetes: horizontal pod autoscaler, or HPA, vertical pod autoscaler, or VPA, and cluster autoscaler, or CA. To create autoscaling, list the current number and state of pods. You have 1 pod in this scenario. A replica set is automatically created when you create a deployment. In order to autoscale, you simply use the autoscale command with the requisite attributes. Min is the number of minimum pods. Notice that we have changed the value of min to 2. Max is the number of maximum pods. And CPU% acts as a trigger that tells the system to create a new pod when the CPU usage reaches 50% across the cluster. In the background, the deployment still uses the replica set to scale up and down. Notice the numbers of replicas in this autoscaled replica set has changed to 2 since the minimum number specified in the previous autoscale command was changed to 2. Now, in Kubernetes, there are 3 autoscaling types. The horizontal pod autoscaler, or HPA, adjusts the number of replicas of an application by increasing or decreasing the number of pods. The vertical pod autoscaler, or VPA, adjusts the resource requests and limits of a container by increasing or decreasing the resource size or speed of the pods. And the cluster autoscaler, or CA, adjusts the number of nodes in the cluster when pods fail to schedule or demand increases or decreases in relation to the node's capacity. In Kubernetes, an HPA automatically updates a workload resource, like a deployment, by horizontally scaling the workload to match the demand. Horizontal scaling, or scaling out, automatically increases or decreases the number of running pods as application usage changes. An HPA uses a cluster operator that sets targets for metrics like CPU or memory utilization and the maximum and minimum desired number of replicas. For example, the system load is low early in the morning, so 1 pod is sufficient. The HPA autoscales the workload resource to meet usage demands. By 11 a.m., peak load drives a need for 3 pods, so the HPA autoscales the workload resource to meet usage demand. Usage drops in the afternoon, so the 3rd pod is marked for deletion and removed. And usage drops even lower by 5 p.m., so another pod is marked for deletion and removed. And another way to enable autoscaling is to manually create the HPA object for a YAML file. Similar to the autoscale command, you can set the minimum and maximum number of pods. The CPU% flag shows up as target CPU utilization percentage. And even though you can create an HPA autoscaler from scratch, you should use the autoscale command instead. A best practice is to scale horizontally, but there are some services you may want to run in a cluster where horizontal scaling is impossible or not ideal. Vertical scaling, or scaling up, refers to adding more resources to an existing machine. A VPA lets you scale a service vertically within a cluster. The cluster operator sets targets for metrics like CPU or memory utilization, similar to an HPA. The cluster then reconciles the size of the service's pod or pods based on their current usage and the desired target. For example, the system load is low early in the morning, so system resources used by the pod are low. By 11 a.m., peak load drives a need for more capacity. The VPA autoscales the pod by adding more system resources, CPU and memory, to meet the demand. Usage drops in the afternoon, so the pod is autoscaled to use fewer system resources. And usage drops even lower by 5 p.m., so the pod is autoscaled further to match the 7 a.m. levels. You should not use VPAs with HPAs on resource metrics like CPU or memory. However, you can use them together on custom or external metrics. A CA autoscales the cluster itself, increasing or decreasing the number of available nodes that pods can run on. Pods are autoscaled using HPA or VPA, but when the nodes themselves are overloaded with pods, you can use a CA to autoscale the nodes so that the pods can rebalance themselves across the cluster. For example, the system load is low early in the morning, so existing nodes can handle the load. When demand increases, new pod requests come in, and the CA autoscales the cluster by adding a new node and pod to meet the demand. By 11 a.m., peak load brings the new node to full capacity. When usage drops in the afternoon, unused pods are marked for deletion and removed. And when usage drops even lower by 5 p.m., all pods in the new node are marked for deletion and removed. And then, the node itself is marked and removed. A cluster autoscaler ensures there's always enough computer power to run your tasks, and that you aren't paying extra for unused nodes. For example, nights and weekends may have fewer development or continuous integration testing loads, and clusters may have periods where all batch processing jobs are complete, and the new batch doesn't start until later in the day. Each autoscaler type is suitable in specific scenarios, so you should analyze the pros and cons of each to find the best choice. Using a combination of all three types ensures that services run stably at peak load times, and costs are minimized in times of lower demand. In this video, you'll learn that autoscaling enables scaling as needed at the cluster or node level and the pod level. You can autoscale a deployment or a replica set. Autoscaler types include horizontal pod, or HPA, vertical pod, or VPA, and cluster, or CA. And a combination of all three autoscaler types often provides the most optimized solution. Welcome to Rolling Updates. After watching this video, you will be able to explain what a rolling update is and how it works, list the pre-steps before a rolling update can be applied, and demonstrate how to roll back a rolling update. Rolling updates are automated updates that occur on a scheduled basis. They roll out automated and controlled app changes across pods, work with pod templates like deployments, and allow for rollback as needed. To prepare your application to enable rolling updates, add liveness probes and readiness probes to deployments. That way, deployments are appropriately marked as ready. Next, add a rolling update strategy to the YAML file. In this example, you are creating a deployment with 10 pods. Your strategy is to have at least 50% of the pods always available. The max surge of 2 says that there can only be 2 pods added to the 10 you defined earlier. For a zero downtime system, set the max unavailable to 0. Setting the max surge to 100% would double the number of pods and create a complete replica before taking the original set down after the rollout is complete. And sometimes, it is also useful to use the mini ready seconds attribute to wait a few seconds before moving to the next pod in the rollout stage. Let's look at a working example of rolling out an application update. You have a deployment with 3 pods in your replica set. Your application displays the message, "Hello world." Your client has submitted a new request, and you have a new image for your application with a different message. Instead of the original text, you need to show "Hello world v2" to your users. But you cannot have any downtime in your application. First, you need to build, tag, and upload this new image to Docker Hub. Your new software has been Dockerized and then updated to Docker Hub with the name and tag Hello Kubernetes upcar/hello-kubernetes:2.0. These are simple Docker commands, not related to Kubernetes at all. Now, apply this new image to your deployment. You have the 3 pods from the first command. The second command sets the image flag to the updated tag image on Docker Hub. The output says the image has been updated. But let's verify if that actually happened. You can see the status of the rollout by using the rollout status command. The API shows deployment hello-kubernetes successfully rolled out. That's great. Now, if you go back to the URL, you will see the new message, Hello World v2. Sometimes there are errors in a deployment, or the client can change their minds. Rollbacks are easy to implement in Kubernetes. Use an undo command on the rollout. Use the get pods command to confirm the rollout pods are terminated. You will also see 3 new pods that are created as part of this rollback. If you visit the site again, you will see the original message, and that's how you roll back challenges to your application. Now, let's take a look at how rolling updates work, both all at once and one at a time. In an all-at-once rollout, all V1 objects must be removed before V2 objects can become active. Here, you see version 1 of an app with 3 pods running that users can access. When version 2 is deployed, new pods are created. The version 1 pods are marked for deletion and removed. User access is blocked. Once the version 1 pods are removed, the version 2 pods become active and user access is restored. Notice the time lag between deployment and pod updates. In an all-at-once rollback, all V2 objects must be removed before V1 objects can become active. Let's see what an all-at-once rollback looks like. Here, you see version 2 of an app with 3 pods running that users can access. When version 1 of the app is deployed, new pods are created. The version 2 pods are marked for deletion and removed, and user access is blocked. Once the version 2 pods are removed, the version 1 pods become active and user access is restored. In a one-at-a-time rollout, the update is staggered so user access is not interrupted. Here, you see version 1 of an app with 3 running pods that users can access. When version 2 is deployed, a new pod is created. The first version 1 pod is marked for deletion and removed, and the V2 pod becomes active. Then, a second V2 pod is created, and the second version 1 pod is marked for deletion and removed. The second V2 pod becomes active. A third V2 pod is created, and the third version 1 pod is marked for deletion and removed. And now, the third V2 pod becomes active. With a staggered update, user access is not interrupted. In a one-at-a-time rollback, the update rollback is staggered, so user access is not interrupted. Let's see what a one-at-a-time rollback looks like. Here, you see version 2 of an app with 3 running pods that users can access. When version 1 of the app is deployed, a new pod is created. The first version 2 pod is marked for deletion and removed, and the V1 pod becomes active. Now, a second V1 pod is created. The second version 2 pod is marked for deletion and removed, and the second V1 pod becomes active. Then, a third V1 pod is created, and the third version 2 pod is marked for deletion and removed, and the third V1 pod becomes active. In this video, you learn that rolling updates roll out app changes in a controlled and automated way. Rolling updates publish changes to applications without noticeable interruption. Rolling updates can roll back changes when an application needs to revert. And rolling updates and rollbacks can be performed using all-at-once and one-at-a-time strategies. Welcome to Config Maps and Secrets. After watching this video, you will be able to identify important config map characteristics, describe config map capabilities, describe 3 ways to create a config map, and describe 3 ways to create a secret. As software developers, a good practice to adopt is to avoid hard-coding configuration variables in application code by keeping the configuration variables separate so that any changes in configuration settings do not require code changes. A config map is an API object that stores non-confidential data in key value pairs and is meant for non-sensitive information as they do not provide secrecy or encryption. In addition, a config map provides configuration data to pods and deployments so that the configuration data is not hard-coded inside the application code. Data stored in a config map cannot exceed 1 megabyte. For larger amounts of data, consider mounting a volume or use a separate database or file service. A config map has optional data and binary data fields, and in this case, there is no spec field in the template, and the config name must be a valid DNS subdomain name. A config map is reusable for multiple deployments, thus decoupling the environment from the deployments themselves. You can create a config map by using string literals, by using an existing properties or key equals value file, or by providing a config map YAML descriptor file. You can use the first and second ways to help create such a YAML file. The deployment or pods consume a config map by using environment variables with the config map keyref attribute, or by mounting a file using the volumes plugin. Kubernetes applies the config map to the pod or the deployment just before running the pod or deployment. You'll use the environment variable directly in the YAML file. The message variable is used in the JavaScript file as process.env.message. Apply this development descriptor to our deployment and the application displays the string hello from the config file. The result is excellent, but the message is hard-coded in the descriptor file. Let's change this situation by using a config map. The simplest way to provide a config map is to provide a key value pair in the center of the config map command. After this first step, the second step is to tell our deployment about the new message variable and specify its location for pickup. You do that by adding the environment section in the deployment descriptor as shown, and using the value from attribute to point to the config map created in the first step. In this case, the deployment will look for a key named message in the config map named myconfig. Another way to add the message variable in the config map is to use a file that contains all environment variables in the key equals value format. Such a file is useful for adding many variables instead of listing those variables one by one on the command line. Here is a file with just one message key and a value hello from the my.properties file. You can now create the config map by using the from file flag. Notice that the key is my.properties in the deployment descriptor section. To use the config map in the server.js file, refer to it as process.env.message.message. Use the describe command to get the YAML output. Then view the environment section. If you specify a directory to the from file flag, the entire directory is loaded into the config map. You can also load a specific file with a key by using the from file equals key equals file name format. Finally, you can use a YAML file with the config map descriptor and apply that file. In our case, we have saved the output from kubectl git config map as a YAML file called my-config.yaml. The first command indicates that there is no config map to begin with. Here, you are creating the config map.yaml file. You'll now apply the YAML file to your cluster, which creates the config map. Note the message in the config map file description. Using the YAML file will get you the same results as the other methods. Now, working with a secret is like working with a config map. First, create a secret using a string literal. Next, the get command verifies that the secret was created. Finally, to prove that our secret is indeed a secret, use the describe command and check that you don't see any secret written using display text. You can print out the secret in YAML format, and you'll see that the value is fully encoded. To use the secret, add another environment to the deployment descriptor as shown, and then use the application key by referring to the application as process.env.api_creds. The screenshot displays the secret along with other environmental variables from the node.js file. Another way to use the secret key in your application is to use volume mounts. Create the same secret as done previously. In the descriptor YAML file, use a volume for the secret with a corresponding volume mount. Each container in the descriptor file has its own volume mount, but shares the volume. The API-creds secret is mounted as a file at etc/API/API-creds, and the application will read and process the file to extract the secret. In this video, you learn that you can use a config map to provide variables for your application. You can create a config map by using a string literal, by using a properties file, or by using YAML. You can use a secret to provide sensitive information to your application. And you can create a secret by using a string literal, by using environment variables, or by using volume mounts. Welcome to service binding. After watching this video, you will be able to explain the roles and goals of service binding, describe how to bind a Kubernetes cluster to an external service, identify commands to retrieve the secrets in your Kubernetes cluster, and describe how to use service binding in apps. So, what is service binding? Service binding is the process needed to consume external services or backing services, including REST APIs, databases, and event buses in our applications. Service binding manages configuration and credentials for back-end services while protecting sensitive data. In addition, service binding makes service credentials available to you automatically as a secret. Service binding consumes the external service by binding the application to a deployment. Then, the application code uses the credentials from the binding and calls the corresponding service. Here, you can see an architectural diagram that illustrates the binding of a Kubernetes cluster to an external service. Next, let's learn the steps required to bind the service to your application. Let's use an IBM Cloud Service example. Service binding quickly creates service credentials for an IBM Cloud service. You create the service credentials using IBM's public cloud service endpoint and then store or bind your service credentials in a Kubernetes secret in your cluster. Here's how to bind an IBM Cloud service to your cluster. First, you provision an instance of the service. Then, you bind the service to your cluster to create service credentials for your service that use the public cloud service endpoint. Next, store the credentials in a Kubernetes secret. Finally, you configure your app to access the service credentials in the Kubernetes secret. The IBM Cloud Catalog provides various services that range from visual recognition to natural language processing and creating chatbots. We are using the Tone Analyzer service to explain binding. This service uses linguistic analysis to detect tone in a given text. The service provides an SDK in JavaScript. You bind the service to the deployment so that the credentials are automatically available. The code then uses the credentials from the binding and calls the Tone Analyzer service. Okay, now that you know the steps, let's examine some code. In the first step, provision an instance of the service by creating the service instance using the command line interface. You can also provision an instance of the service by using the catalog on the IBM Cloud website. In the second step, you bind this newly created service instance to your cluster by using the service bind command. IBM Cloud Service Binding automatically creates a Kubernetes secret with the service credentials. The credentials of a service instance are base64 encoded and stored inside your secret in the JSON format. And now that the service is bound to your cluster, here in step 3, you can verify your secret object. The getSecrets command shows all the secrets in your Kubernetes cluster. Or, you can retrieve the same secrets in the Kubernetes dashboard user interface as well as on the IBM Cloud Kubernetes service. To access the data in your secret, choose one of the following options. Mount the secret as a volume to your pod based on the specifications provided in Step 1. This action creates a JSON formatted file named binding that is stored in the volume mounts directory. The binding file includes all information and credentials required to access the IBM Cloud Service. Or you can reference the secret in environment variables. The environment variables binding, API key, binding.username, and binding.password correspond to the API key, username, and password of the Watson Tone Analyzer service instance created in the previous step. The displayed code snippet shows a sample node.js application using the binding.api key, the binding.username, and the binding.password environment variable inside an express.js application that will be deployed to the IBM Cloud Kubernetes service. In this video, you'll learn that binding an external service to your deployment automatically provides the credentials to use the service inside the code. Credentials are stored as a secret that can be consumed using volume mounts and volumes. Binding manages configuration and credentials for back-end services while protecting sensitive data. And you can configure your app to use the credentials stored in the secret, either by mounting the secret as a volume to your pod or by referencing the secret in environment variables. Welcome to Introduction to Red Hat OpenShift. After watching this video, you will be able to explain what OpenShift is and list its features, describe OpenShift CLI, architecture, and components, and compare OpenShift with Kubernetes. OpenShift, developed and supported by Red Hat, is an enterprise-ready Kubernetes container platform built for the hybrid cloud strategy. It provides a consistent application platform to manage hybrid, multi-cloud, and edge deployments. It is built on the technological foundation of Linux, containers, and automation. It provides full-stack automated operations and self-service provisioning for developers to efficiently move ideas from development to production. And besides container orchestration, it provides additional tooling around the complete lifecycle of applications, from build to CI/CD to monitoring and logs. Both Kubernetes and OpenShift are container orchestration platforms. Kubernetes is a critical component of OpenShift. OpenShift is used as an extension of Kubernetes to provide a more robust and comprehensive platform for containerized applications. Let's review the features of OpenShift. Apps can scale to thousands of instances across hundreds of nodes in seconds. Flexible hybrid infrastructure options simplify deployment and management. Open source standards use Kubernetes and Open Container Initiative (OCI) containers, which means development is familiar and containers are portable across multiple environments. It includes a comprehensive set of developer tools, multi-language support, command line, IDE integrations, and more. It supports over-air platform upgrades, and services from the Operator Hub can be fully configured and deployed with one-click upgrades. Container and app builds, deployments, scaling, and health management are streamlined and automated. OpenShift also enhances support for smaller footprint topologies in edge scenarios for better mapping, connectivity, and availability. It easily manages and enforces policies across multiple clusters at scale. It offers access controls, networking and enterprise registry, built-in scanner, enhanced threat detection, lifecycle vulnerability management, and risk profiling. OpenShift supports enterprise persistent storage solutions for running stateful and stateless apps. And the OpenShift partner ecosystem provides additional storage and network services, as well as IDE, CI, integrations, and more. Let's compare the main aspects between OpenShift and Kubernetes. OpenShift is a product while Kubernetes is an open source project. Installation on OpenShift has limited options after the installation starts, while Kubernetes is installable on every Linux environment. OpenShift is less flexible, while Kubernetes is more flexible. OpenShift is available online with Azure and dedicated, while Kubernetes is available on EKS, on AWS, GKE on GCP, and AKS on Azure. OpenShift image streams provide better management, while Kubernetes container image management is not that easy. OpenShift has a very strict security policy, while Kubernetes security maintenance is easy. OpenShift router objects permit external access, while Kubernetes ingress objects permit external access to Kubernetes clusters. OpenShift uses the less flexible deployment config command, while Kubernetes uses more flexible deployment objects. OpenShift provides a good user experience, while Kubernetes requires extra tools for a better user experience. OpenShift provides good networking solutions out of the box, while Kubernetes provides third-party plugins when network solutions are unavailable. OpenShift provides a good service catalog, while Kubernetes offers less provision for better services in clusters. OpenShift has a user-friendly web console layout that is easy to learn for beginners, while Kubernetes console layout is difficult to learn for beginners. And the OpenShift CI and CD integrate with Jenkins, while the Kubernetes CI and CD can be integrated, but not with Jenkins. OpenShift runs on top of a Kubernetes cluster, with object data stored in the etcd key value store. It has a microservices-based architecture. Its services are REST APIs, which expose the core objects, and controllers, which read the REST APIs, apply changes to the other objects, and report status or write back to the object. They also maintain the cluster desired state. Docker provides abstraction for packaging and creating Linux-based, lightweight container images. Kubernetes provides cluster management and orchestrates containers on multiple hosts. OpenShift features add management of source code, builds, and deployments for developers, managing and promoting images at scale as they flow through your system, application management at scale, team and user tracking management of a large developer organization, and networking infrastructure that supports the cluster. In an OpenShift environment, the Kubernetes master runs on Red Hat Enterprise Linux Core OS, while worker nodes support Red Hat Enterprise Linux, that is, the Red Hat base layer. Next is the Kubernetes architecture and a set of services. Cluster services include integrated monitoring, a private registry within the cluster, networking solutions, and many others. Platform services help users manage their workloads. Application services help users build cloud-native apps. And developer services increase developer productivity. OpenShift offers a set of command line interface, or CLI, tools that lets users perform various admin and development operations from the terminal. OpenShift CLI, or OC, is the most commonly used CLI tool to perform end-to-end operations. It runs on Windows, Linux, or Mac. OC lets you work directly with project source code using command script OpenShift operations, and manage projects during restricted bandwidth or availability of the web console. Since OpenShift runs on top of a Kubernetes cluster, a copy of kubectl is also included with OC. The OC and kubectl binary offer the same capabilities, but OC is further extended to natively support OpenShift features, such as deployment configs, build configs, routes, image streams, and image stream tags. These are not available in standard Kubernetes. OC also offers an inbuilt login command for authentication. And additional commands, like new app, are also supported by OC, which makes it easier to get new applications started using existing source code or pre-built images. In this video, you learn that Kubernetes and OpenShift are container orchestration platforms. OpenShift is an enterprise-ready Kubernetes container platform built for open hybrid cloud. OpenShift runs on a Kubernetes cluster with object data stored in the etcd key value store. And OpenShift is easier to use, integrates with Jenkins, and has more services and features.
Welcome to Builds. After watching this video, you will be able to describe what a build is, build input sources, and build strategy. Describe what image streams do and identify their features. Explain how to automate builds using build triggers. List the steps used for the build config process, and explain source to image, Docker, and custom build strategies. A build is the process of transforming inputs into a resultant object. For example, transforming source code to a container image. A build requires a build configuration file, or build config, which defines the build strategy and input sources. Commonly used build strategies are source to image, or S2I, Docker, and custom. A build input source provides content for builds. You can use the following build inputs listed in order of precedence: inline Dockerfile definitions, content extracted from existing images, Git repositories, binary or local inputs, input secrets, and external artifacts. Note that multiple inputs can be combined into a single build, and an inline Dockerfile takes precedence and overwrites any external Dockerfile. An image stream is an abstraction for referencing container images within OpenShift. An image stream continuously creates and updates container images, but does not contain actual image data. Instead, it points to images stored in internal and external registries or to other image streams. A single image stream can consist of many different tags, such as latest, dev, and test, and each tag points to a certain image in a registry. To deploy an application, you'll refer to the image stream tag rather than hardcode the registry URL and tag. If the source image location changes, you'll update the image stream definition rather than individually updating all the deployments. An image stream also provides a trigger capability that automatically invokes builds and deployments when a new version of an image is available. Rather than running builds manually, automate the process using triggers. Webhook triggers send a request to an API endpoint, and they also support generic webhooks and the more often used GitHub webhooks, which send the trigger request to the API endpoint on any new commit or a pull request or other circumstances. Next is the image change trigger, which triggers builds when a new version of an image is available. For instance, if you build your application using a Node.js base image, that image is updated when security fixes are released and other updates occur. Finally, a configuration change trigger causes a new build to run when you create a new build config resource. Let's look at a sample configuration file for build config. The specification creates a new build config named ruby-sample-build. The run policy field controls how builds created from a build configuration need to run. Values include the default serial or sequentially and simultaneously. You can also specify a list of triggers that creates a new build. The source section defines the build's source, and the source type determines the primary input, like a Git repository, an inline Dockerfile, or binary payloads. The strategy section shows which strategy was used to execute the build, such as source, Docker, or custom strategy. This example uses the Ruby-20 CentOS 7 container image and source to image, or S2I strategy for the application build. So, after you build the container image, it is pushed into the repository described in the output section, and the post-commit section defines an optional build hook. Another build strategy offered by OpenShift is called Source to Image, or S2I. The S2I tool builds reproducible container images and injects a container image with the app source to produce a ready-to-run image. The new image is built by incorporating a builder image plus the source that avoids using a Dockerfile, which enables going from source to image in a single step. OpenShift comes with a variety of available builder images, saving you time and development effort. Using a Docker build strategy requires a repository that contains a Dockerfile and the necessary artifacts. When you kick off a build, OpenShift takes the input, invokes the Docker build command, and creates an image, which is then pushed to the internal OpenShift registry. Here are 4 ways to implement the Docker build strategy. Replace Dockerfile from image, use Dockerfile path, use Docker environment variables, or add Docker build arguments. In a custom build strategy, you must define and create your own builder image required for the build process. Custom builder images are regular Docker images that contain the logic needed to transform the inputs into the expected outputs. Both Docker and S2I strategies result in runnable images, but the custom build strategy creates additional objects, like jar files and CI/CD deployment that performs unit or integration tests. Custom builds are only available to cluster administrators because they run with high privileges. Cloud-native development requires greater automation throughout the container lifecycle. Automation is available using the continuous integration and continuous delivery pipeline, or CI/CD. For example, the OpenShift CI/CD process automatically merges new code requests to the repository, then builds, tests, approves, and deploys a new version to different environments. In this video, you learned that a build is a process that transforms inputs into an object. Build inputs in order of precedence include inline Dockerfile definitions, content extracted from existing images, Git repositories, binary or local inputs, input secrets, and external artifacts. An image stream is an abstraction for referencing container images within OpenShift. You can automate builds using a webhook, image change, or configuration change trigger. Commonly used build strategies include source-to-image, or S2I, Docker, and custom build strategies. And finally, builds require a build configuration file, or build config, which defines the build strategy and input sources.
Welcome to Operators. After watching this video, you will be able to define an operator and explain its purpose, show the relation between custom controllers, the operator pattern, and custom resource definitions, or CRDs, and explain the purpose of the operator hub, framework, and maturity model. Operators automate cluster tasks and act as a custom controller to extend the Kubernetes API. Operators run in a pod and interact with the API server, package, deploy, and manage Kubernetes applications, and automate app creation, configuration, and management via continuous real-time decisions. Operators package, deploy, and manage native apps in Kubernetes, automate other tasks, and ensure all relevant components are included. There are human operators and software operators. Human operators understand the system they control. They know how to deploy services and how to recognize and fix problems. Software operators try to capture the knowledge of human operators and automate the same processes. Operators provide ease of repeatable installation and upgrade processes, regular full system health checks of each component in the system, over-the-air or OTA updates for components and software vendors' content, a way to collect and spread knowledge from field engineers to all users, and integrations with APIs and CLI tools such as Kubectl and OC commands. Let's see how service brokers compare with operators. Service brokers provide a short-running process that cannot perform the consecutive day's operations, such as upgrades, failover, or scaling, customizations and parameterization only at the time of installation, and off-cluster services. Operators provide a long-running process that can perform operations like upgrades, failover, or scaling every day, customizations and parameterizations as operators constantly watch the current state of your cluster, and off-cluster services. Custom resource definitions, or CRDs, store and retrieve objects in the Kubernetes API. CRDs extend Kubernetes functionality beyond built-in resources like deployments and pods. They make the Kubernetes API more modular and flexible. Users can install CRDs in clusters, but each CRD is available only in the cluster it is installed. And once installed, CRD objects are accessible using Kubectl, similar to pods and other resources. To change the state of a cluster, custom controllers are used. Controllers reconcile a cluster's actual state with its configured state. Custom controllers do the same reconciling for custom resources. Combining CRDs and custom controllers creates a declarative API. This combination is known as the operator pattern. Custom controllers interpret CRD data as the desired state and reconcile a cluster's actual state to match the CRD data. The Operate framework is an open-source toolset that covers coding, testing, delivery, and operator updates. The Operator SDK, which includes Helm, Go, and Ansible, helps authors build, test, and package their operators without requiring knowledge of Kubernetes API complexities. The Operator Lifecycle Manager, or OLM, controls the install, upgrade, and role-based access control, or RBAC, of operators in a cluster. The Operator Registry stores CRDs, cluster service versions, or CSVs, and operator metadata for packages and channels. It runs in Kubernetes or OpenShift clusters to provide the operator catalog data to OLM. The Operator Hub web console lets cluster administrators find operators to install on their cluster. The sophistication of operator management logic varies depending on the type of service represented by the operator. This operator maturity model defines the phases of maturity for general day 2 operation activities and ranges from basic install to autopilot. It also shows which activities are supported by the Helm, Go, and Ansible capabilities of the Operator SDK. Some operator examples include deploying an application to the OpenShift cluster. This can go beyond deployments to include secrets, config maps, and storage resources. Scaling the application with the help of multiple replicas based on the application type. Automation of rote tasks in a cluster, like taking and restoring backups of an application state, and integration. Let's consider more about the first example. To deploy a whole application, create a custom resource for that app, and then a custom controller for that CRD. The operator logic determines how to reconcile the actual and configured states. A CRD requires the creation of deployments, services, storage, and other objects. The Operator Hub view of the OpenShift web console enables operator installation with one click. Operator Hub has many different types of operators available, including Red Hat operators, certified operators from independent service vendors partnered with Red Hat, community operators from the open source community but not officially supported by Red Hat, and custom operators defined by users. You can install many tools from the Kubernetes ecosystem via the Operator Hub. An example is the Istio Service Mesh. In this video, you learn that CRDs extend the Kubernetes API. CRDs paired with custom controllers create new declarative APIs in Kubernetes. Operators use CRDs and custom controllers to automate cluster tasks. The Operator framework covers coding, testing, delivery, and updates. And the Operator maturity model defines the phases of maturity for activities. Welcome to Istio. After watching this video, you will be able to describe a service mesh, identify the 4 concepts that Istio supports, describe the benefits and challenges of using Istio with microservices, and identify the 4 basic communication service monitoring metrics. A service mesh is a dedicated layer for making service-to-service communication secure and reliable. Among other things, service meshes provide traffic management to control the flow of traffic between services, security to encrypt traffic between services, and observability of service behavior to troubleshoot and optimize applications. The service mesh term describes the software that creates a security or network domain with a pattern for achieving the above capabilities. Istio is a platform-independent service mesh often used on Kubernetes. In keeping with the definition of a service mesh, Istio exhibits these 4 concepts. First, there's connection. Connection enables Istio to intelligently control the traffic between services in canary deployments, A/B tests, and other deployment models. Next is security. Istio secures services through authentication, authorization, and encryption. Istio also provides enforceability and provides control by enforcing policies across an entire fleet. And finally, Istio supports observability. Using Istio, you can observe the traffic flow in your mesh, trace call flows and dependencies, and view metrics such as latency and errors. Istio features transport security layer encrypted communications between services in a cluster, combined with the appropriate authentication and authorization. Istio load balances traffic for different protocols, including HTTP, TCP, gRPC, and WebSocket traffic. Istio supports granular configuration of traffic flow, known as routing rules, and supports control with continuous REST trees, fault injection methods, and automatic failovers. Along with policies and API support for access controls, rate limits, and quotas, Istio also provides automatic monitoring, logging, and tracking of both inbound and outbound traffic. Istio is extensible and can handle a diverse range of deployment needs. Istio runs on Kubernetes, where you can add applications of a cluster to the mesh, extend the mesh to additional clusters, or connect to virtual machines or other endpoints running outside of Kubernetes. Next, let's check out how Istio works with microservices. There are two main components in Istio, the control plane and the data plane. Communication between services is handled by the data plane. If a service mesh is absent, the network cannot identify the type of traffic that flows, the source, or the destination, and cannot make necessary decisions. All network traffic is subject to, or intercepted by, a proxy called envoy, which is used by the service mesh and allows many features depending on the configuration. The control plane takes the desired configuration and its view of the services and dynamically programs and updates the proxy servers as the environment changes. A cornerstone of cloud-native development is microservices architecture. Microservices are a cloud-native architectural approach in which a single application contains many loosely coupled and independently deployable smaller components or services. Microservices have well-defined APIs for communicating with each other. The benefits of microservices are multiple. Code updates are easy, as only the relevant service needs to be updated instead of the entire application. They allow teams to use different technology stacks for each component. In addition, components can be scaled independently instead of the entire application. Challenges of microservices include encryption of traffic to ensure secure communication. Development teams might want to roll out new features to a subset of users or compare two versions of features in their application to see which engages users the most. In these cases, teams need canary deployments and A/B testing. The communication between microservices also leads to cascading failures if one service is unreachable or particularly slow. Developers need retries and circuit breaking to prevent errors in one microservice from cascading to others. Consider the application architecture shown on the screen, in which the UI talks to an ordering microservice. The ordering microservice interacts with the inventory microservice, which then talks to a database. Service-to-service communication enables any microservice architecture, but as that communication gets more complex, a service mesh can help improve it. Let's check out some more of Istio's capabilities. Istio performs traffic shifting by gradually migrating the traffic from one version of a microservice to other versions. So, say a team working on the ordering microservice has a new update to that microservice. The team begins by sending 5% of traffic to that second version, and over time, the team can increase this to 50% and eventually to 100%. Similarly, Istio request routing allows you to perform A/B testing and direct a particular version of a microservice to a subset of users while sending the original version to the remaining users. The process ensures that a new version increases user engagement or performance. Istio also provides a variety of security measures for your microservices, including encryption. Istio defends from man-in-the-middle attacks by encrypting traffic between microservices. In addition, Istio makes it easier to implement policies for service access control so that services can only talk to the other required services. In this example, the UI service would be unable to directly communicate with the inventory service, even if it tried. Among other metrics, Istio provides service communication metrics. These metrics cover the 4 basic service monitoring needs: latency, traffic, errors, and saturation. For example, Istio provides metrics on request counts so that you can see how much traffic your requests are receiving and request duration, shown here in seconds, so that you can find bottlenecks and ensure that there are prompt responses. In this video, You learned that a service mesh provides traffic management to control the flow of traffic between services, security to encrypt traffic between services, and observability of service behavior to troubleshoot and optimize applications. Istio supports the 4 concepts of connection, security, enforcement, and observability. One of the examples where Istio is commonly used is with microservices applications, and Istio provides service communication metrics for basic service monitoring needs, including latency, traffic, errors, and saturation.